Okay, so in this homework here, did it make sense, this idea of local versus global processing? Right, this thing has these preference rules in the homework you just did. And they look at, you're sort of at the whole piece of music. Even when you just look at these dots here, when it's trying to figure out, well, what are the strongest beats? Right? That's it's like taking a vote. Every note contributes to this decision. Right? It doesn't just start at the beginning and try to figure out, oh, are these pickup notes? Right? It figures out what are the strongest beats and then figures out where the bar lines are, and from that it falls out that, yes, these are pickups. But how does it know that the bar line is here and not at the beginning? Well, by looking at long notes. Looking at how long notes are and other things. Like it knows that chord spans, that like to start on strong beats. And all these things combine together. So it's not just one thing. It's not just note lengths. And it's not just, in this case, chord spans. I mean, that's not even a duration-oriented thing, right? That's actually something from pitch. You're analyzing what key are you in, and those key changes tend to happen on strong beats. But all these different things, I don't know how many rules there were, maybe 10 or a dozen or something. However many rules there were in this paper, they're preference rules. This is nice when this happens, but it doesn't always have to happen exactly that way. An obvious example here is like, look, here's a long note on the strong beat, and that's great. But here, you have one of the longest notes, almost the longest note possible in this piece. And it's on a really weak beat. And that's okay. Because it doesn't happen very often. In fact, that's what makes the music interesting, right? What makes music interesting a lot of the time is the exceptions to the rules. You follow the strict set of rules and then you break them at the right times. Anyway, so that's a very long note, and it's very forgiving to that. So the global processing is super important on lots of different levels here. What I really like is that these are compatible and easy to understand rules. That one rule doesn't wipe out the other rule. All these rules get along. And they're all things that seem common in music. And there's funny exceptions, like here it says it decided here. This is a key change here on a pretty weak beat. Again, it's okay if that happens once in a while. It doesn't mind that. And that's just what it decided to do there. What else can I say about this? Were there questions about this? Anybody had something they wanted to ask about it? Did you, let's see, what else here? How to figure out, how does it know that it's not 3/4 time instead of 2/4 time? Again, it's just by all these rules working together. It's just trying to figure out, which beat tends to be the strongest. But it doesn't just look at rhythmic patterns, which is, I wrote, I've written papers about that, and when this came out, I said, yep, this is a lot better than what I wrote. So, this is a very nice combination of things. There is this interesting thing with pips. In MIDI, because we've been talking about MIDI recently, where you want, people are worried about, 1 millisecond granularity, which is about what MIDI is, for individual events. You don't actually get that because your operating system doesn't actually do that. Even when your sound card says it only takes 14 nanoseconds to go through our sound card, well, still has to go through the operating system and get into Ableton or whatever you're using. So all of a sudden those things are orders of magnitude larger. So be careful of advertisings. And again, even in those programs, you can turn down those FIFO cues. You can turn down the delay in them, but then if you're much more likely to stumble during a performance and to hear bad output. So there's all sorts of trade-offs there. What's interesting here is these are 35 millisecond pips. So, they're for time quantization, right? I don't know if you caught that in the paper, but they're for time quantization. So it's kind of interesting for simultaneity. This sort of gives you an idea of, if you're going to play a chord, about how simultaneous are those notes if you want to catch most cases. And 35 milliseconds is that, which is quite a bit bigger than 1 millisecond. So it's actually kind of a nice reference after having seen the MIDI stuff. Any questions about that? People like the paper okay? Did it make sense? Was the music theory okay? Yeah, I mean, well, you're a band player, if I remember right? Not a very good one, though. Oh, well, okay. Join the club. Well, I'm not a band player at all, so. Yeah. Now, this is a cute thing. And, there's lots of little problems in this. Well, for instance, the thing doesn't know that the last thing can't possibly be a half note. It'll just be a dotted quarter just because there's a pickup bar. But these are all sort of minor things. And when you're looking at the underlying, like, wow, look at all this stuff. So just having more rules, that's nice. Maybe you can grow it more. But just getting the underlying stuff for a pretty wide variety of musics, this works for, actually. It's pretty surprising how well this algorithm works. All right. Okay. So let's do that. At the end of this handout, there is a midterm sample exam. Be careful with that because it is from a different semester. And there's also a second sheet up there if you didn't get it, or it's also an email, of the actual lectures that are going to be on the exam. And it's not that I dislike the other lectures. Like you'll see, gee, the MIDI lectures aren't even on this exam. I don't know, I got asked different questions in last semester, and MIDI is a super important topic. I hope you listened. I hope it was interesting, but can't test everything. And it's just a problem with a class like this. There's too many topics, right, if you do a survey class. And normally, when I was a student, a survey class just wouldn't have exams. But we're not allowed to do that anymore. We are required to torture you, so we do. So anyway, so there's a list of lectures that I'd like you to go over again, go over your notes, try to figure things out, and just take the time to write a good cheat sheet. Because it's kind of good to look through things again. I mean, many of these topics you might see again in 10 or 15 years, but to review them a little bit now might cement them in your brain better. So, cool. Today's topic is the last one that's going to be on this exam. This is the last part of our whirlwind tour of psychoacoustics. It is about, what musicians would call dynamics. We're going to do these things here. We're going to study intensity level, loudness level, and loudness. And I apologize for these names. This is probably one of the reasons why engineers, or actually some of this is psychoacousticians' problem. But anyway, somebody is very unimaginative in their naming here, unfortunately. So it's a little bit confusing that like loudness level and loudness are different things. I don't know, adding the word level to something to change what its unit seems a very sad approach to naming. But anyway, it is what it is, and we'll just talk about it. The first thing is we're going to talk about intensity. Intensity is in watts per meter squared, and we have this equation, I equals Ka squared. Okay, so what is that? Well, A is just the amplitude. Like the most common amplitudes you see are graphs, like in the very first homework assignment, right? There were the trumpet graphs. There were amplitudes there. You'll notice something that, like the time axis, I made a comment about this here, the time axis is clearly labeled in seconds. The amplitude axis isn't, right? It's just some arbitrary units. You know they're linear. I mean, it's linear amplitude, but that's about it. So why is that? Why, if we have a frequency axis or a time axis or whatever other axes, we're always really careful about the units, but amplitude, it just says amplitude. And so the issue here is, it is actually possible to measure something in watts per meter squared, an intensity. But you almost never do that in electronic music. It's very rare to run into that, at least in timbre graphs and graphs of samples. For instance, if you're in a sample library and it's showing you the amplitude of the samples, why doesn't it tell you what the units are in watts per meter squared? Well, it has no idea how your amplifier is set up, right? If you're playing it quietly, it's a lot fewer watts per meter squared than if you crank up your volume, right? You always have this amplifier between you and the person And also, like, is the person right next to the speaker or far from them? You know, there's so many unknowns in this whole thing that they just, you just say, hey, this is the amplitude, and you forget it. Similarly, on the input, like for that trumpet paper, they don't know what the watts per meter squared was on their inputs. They had a microphone preamp, and they turned the microphone preamp until the volume was good, so they got a good recording. So they just don't know. So it's this weird thing that, you know, engineers like to be extra careful about everything, but then we have, you know, amplitude or sample value is just sort of this arbitrary unit. In any case, this K here is what converts from the arbitrary unit to intensity, right? So the K is where all that stuff goes. That's your, K stands for kludge factor. No, I don't know what it stands for. It stands for something. So K is a constant that converts to real units from A as some linear quantity, which is often volts if you're looking at a scope, or sample values, something linear. Okay, so and good for intensity? Okay, so then the next thing is intensity level. So we're going to add the word level. What that means is that we're going to do decibels. So it's a bit problematic here. I mean, instead of intensity, you can say watts per meter squared if you want, or whatever the actual units are. For intensity level, you can't give any units. You can say it's in dB, right? But dB isn't a unit. No more than degrees radians. You know, radians isn't, or degrees. Those aren't units, right? You can't take cosine of apples or cosines of oranges. You take cosines of a number. It has to be unit plus what's inside a cosine. So it's this icky thing. You know, we're used to having units for things, but actually it really matters if you're taking cosine of something in radians or cosine of something in degrees. So it's a thing that matters, but it's not units. Anyway, so we have intensity level in dB. Why is it unitless? Well, because you have I over I ref in here. It's a ratio, and the units cancel because I ref has the same units as I does. So I ref is 10 to the minus 12 watts per meter squared, and we call that 0 dB intensity level. And it's sort of an arbitrary thing, 10 to the minus 12. You know, what is that? It just turns out that for the average human, that's barely audible sine wave at 1,000 hertz. I'm probably not an average human anymore. I'm too old. But most of you, unless you've been listening to loud rock and roll, you are, or some other very loud sounds, that you have this 0 dB intensity level at 1,000 hertz. So that's something to know. 40 dB is moderately loud, maybe a quiet speaking voice. I'm certainly talking louder than that. And then 120 dB is where, you know, about where most people hear pain. So those are just things to know. This I over I ref, it's just something people agreed on. Is this approximate? Yeah, but it's not too bad. You know, it's a lot better than than nothing, right? You know, so you often see like dishwashers will say 40 dB noise or something, and that's a lot different than like our current microwave, which sounds like a vacuum cleaner. I didn't even know to check that. I didn't know they made microwaves that loud anymore. That's, you know, those are the units here that we're talking about. Yeah, so this barely audible at 1,000 hertz, the units are sort of unspecified in the sense that a microwave makes a lot of different sounds, as does your dishwasher, right? There's glurks, and there's low sounds, and there's high sounds, and all sorts of things. And this is a measured thing. This isn't how much your ears actually pick up. This is something you can easily measure if you have the right test equipment. So you got to take it a bit with a grain of salt. On the other hand, hey, it's measurable and it does relate to things. 40 dB intensity level dishwasher is great. If our lawnmowers in the neighborhood had that loudness, we'd actually have quiet days in the summer. You know, these numbers do mean something. There's an interesting here. Why does it say, for those of you who've done dB before, why does it say 10 log I over I ref instead of 20 log? You see both, but why does it say 10 log sometimes? Why does it say 20 log sometimes? Anybody happen to know? It's sort of this dumb, embarrassing thing that you find out, hopefully not in front of other people. But in any case, yeah, all it is this is intensity. This is watts per meter squared, right? So if you're doing this computation with linear amplitudes in here, if you sort of skip this in between step, then you need the 20 log, right? Because the meter, because this has the a squared in here, so that squared factor can move to the outside if you're doing a log of amplitude over amplitude ref. But you're not doing that. You're doing intensity over intensity ref. And that's why it's decibels, right? This is sort of where it came from. Often people skip that in between steps, so you see 20 log. But it's just something to know because it's silly, simple math. Okay? We good? All right. So now we're going to do loudness level. We've done the I and the IL, and now we need to replace an I with an L. We only like 2 letters, I's and L's, in this topic for whatever reason. So now we have loudness level. And this is cool. This is probably the core of what we're doing today. Maybe I don't know if this is still readable. I'd sort of like to get all my scrawl on there. Is that still readable, or is that too small now? Okay. Okay, so loudness level. Okay, first of all, loudness level has units of phones. Now, phones are psychoacoustic units. They're they can only be determined by testing humans, right? So they're standardized because many people have done the tests, and they're averaged over many different listeners and all that kind of great stuff. So it's a real thing, but these are psychoacoustic units. Why do we even talk about this in engineering class? I mean, there's a psychoacoustics department. You can learn this for real in real courses. One of the reasons is that it's actually often useful not just to know about these units, but even convert to these units or some approximation thereof to do signal processing. Often you can actually get way better results out of the same algorithm you would normally use, except use on psychoacoustic units instead of on something easier to measure. Okay, so these psychoacoustic units were measured on humans, and you can only arrive at them through humans. But then now there's conversion factors and tables. I mean, this is old. This is showing us a table, and of course you can get this as a set of formulas online too. So you can do the intensity level measurement and then convert that intensity level measurement by computer without having to involve any human test subject into psychoacoustic units. Do your processing, then convert back to your real world units or whatever your physics units, and that can be useful. So what is this graph? There's a lot of stuff on here. First thing is, hey, on the left side here it has intensity level, like we just talked about. But on the right side, it has intensity. And they're just different units for the same thing. So you can start from here or start from here. It's just something to notice, for the vertical axis. I like to ask something about this on exams, so it, might save you a step by not having to convert intensity to intensity level if you can just read it off here. Then the biggest single thing here is loudness level. Here is the core of thing that people forget. There has to be some anchor point. Like these psychoacoustic units, there's always some reference to physics or engineers units. And that reference then, so in this case here, loudness level is identical to and defined to be intensity level at 1,000 hertz. And that's really, really, really important to understand. Okay, so at 1,000 hertz here, if you have a frequency at 1,000 hertz, loudness level and intensity levels are the same value by definition. So that's sort of the anchor point for loudness levels. And then what they did is they did a bunch of tests, and they played something at 1,000 hertz, where they know the intensity level. That's something that's well defined. And then they played something at some other frequency, and they said, are these the same, or is one louder than the other? And did that thousands upon thousands of times. And then, got this graph of these funny lines. okay? Because your hearing is not a straight FFT, it's not perfectly linear, it's not any of those things that an engineer would like. So it doesn't work the same as your oscilloscope or as your other test equipment. So, okay, so what's next here? Yeah, so loudness level equals intensity level at 1,000 hertz. Keep track of this axis here, right? This is a logarithmic axis. We like to label things in frequency. In music, we actually have note number units, and octave units and stuff, and we could use those, but engineers doing music usually don't. You know, it's just, you'll notice like some of the spectrograms and stuff, we had the vertical axis actually labeled in musical units, but that's unusual. Usually engineers like to do this. But then you have to be careful when you read this graph that you don't screw up reading a semi-log graph. Or, you know, on this axis, is this logarithmic or not? Well, it depends. If you're on this side, it's linear, right? It's linear in intensity level. On this side, it's logarithmic in intensity. So that sort of depends on how you can argue that with the philosophers. I don't know. In any case, this is log frequency here. So at 1,000 hertz, they're the same. And now what you'll notice here is if you go up, you can actually hear lower intensity levels. You're more sensitive here. When this dips down, that means it's more sensitive. Your hearing is more sensitive at say 2,500, 3,000 hertz here. More sensitive than at 1,000 hertz. Okay? And that's true like all the way up, even as you go louder. That's your most sensitive thing. Now, it turns out that many of the formants that you listen to when you listen to speech are, many of the important formants are right in this range. So, of course, there's the question, well, do you speak that way because that's how you hear, or do you hear that way because that's how you speak? I don't know. It was either the chicken or the egg that was first. But why is this dip here? There's a simple answer for that. It's just a resonance of the outer ear canal. Your ear is just, extra sensitive there. And it's a physical thing. Resonance of your outer ear canal. Well, people have different sized heads. That's true, but they're not that different. Somebody with a small head and big head I guess means something different. But somebody with a smaller big ear canal, they're close enough for a graph like this. Okay, so there's this thing here, and then as you go up higher, at 5,000 hertz, 6,000 hertz, you can see very quickly between 5 and 6,000 hertz, normal, it has much less sensitivity. By 6,000 hertz, are same as 1,000, and then it keeps going less and less sensitive until when you get to like 18,000 or whatever that is there, it's out of your hearing range. Some people can hear that, some people can't. Right in this range here, flyback transformers for poor people. I can hear that walk into rooms in this building and what's that noise? Where nobody else hears it. Anyway, that makes sense so far, right? So let's go the other direction. As you go lower in frequency, your threshold of hearing, as it's called, or your zero loudness level, zero phones, is called. That line is also called the threshold of hearing. Is way less, right? So for you to hear low notes, they have to be much louder, much higher intensity level. Especially once you get below 500 hertz or 100 hertz. But this is also getting, it's getting quite low. But these are, and much of the reason, as we talked about before, when we were talking about tuning, when you're at 30 hertz, most physics of instruments can't even generate anything down there anyway. So what you're hearing, and the reason it's loud down there is not actually because there's energy down there, it's because you're hearing all the harmonics. So psychoacoustics has all sorts of other stuff that isn't directly, this graph doesn't have everything about your hearing in it, but it's got some pretty interesting things. Good so far? So when you're looking at the low end here, it is interesting because as you get louder volume, if you have something like 90, 100, like loud talking, maybe what I'm doing, maybe not quite that loud. But anyway, once you get up here, it turns out, hey, the low frequencies aren't too bad. It's only quiet low stuff that's really hard to hear. All right. Questions about this? How many people have seen this before? Oh, okay. And you're still awake. See, that's the advantage of a coffee drink. So, Cool. Yeah. So yeah, these are things to know. Know about the resonance. Know about that low frequency, low amplitude stuff or low intensity level stuff is hard to hear. Know that at 1,000 hertz, they match. So here is a quiz question for you. What is the loudness level for an 80 hertz sine at 60 dB intensity level? This is really silly, but do this exercise now so you know. I got to ask you something on the exam, and I don't want you screwing up reading these silly graphs. So loudness level being phones. Anybody have a guess of how many phones it is? Yep, nobody in the peanut gallery. All right, well, I won't put you on the spot, but here you go. 60 dB intensity level. That's this line here, right? Because make sure you read it. Intensity level is this line. That's great. Then you've got 80 hertz sine wave. Well, yeah, this is confusing as you got 20, 30, 40, 50, 60, 70, 80, 90. I would always count these things because it's so easy. Actually, the original here, I even had the wrong units here. I fixed it. So if you ever look this up, it says 0 there, which makes no sense. On the log scale, you don't really get to that. Anyway, it doesn't matter. So here you have 80 hertz. You go up to here, right? And it's just below this line here, which is 30 phones. Okay, but you're just below, so say 29. I know you guys didn't grow up with slide rule, and those are old and quaint, but I did, and that's what you learn in a slide rule is you can always estimate a little better. Right? Don't say 30. Come on. It's clearly not 30. It's just below it. So say 29. Is it really 28.5? I don't know, but 29 is better than 30. Are we good? Does that make sense? And unfortunately, I got to ask you something on exams, and people get mad because I have all these conceptual questions. So then I try to make, plug and chug questions. Well, I don't know. So you have graph reading, and it's easy to screw up your graph reading. You got to do something on an exam. So please be sure you can do that. All right. There is one final thing I want to mention here, which is unfortunate, I have to say, and that's these pianissimo and fortissimo markings. I'm sorry, that's just dumb. I expect neither Fletcher nor Munson were musicians. I don't know, but anyway, dynamics in musical instruments vary all over the place. And there is no, like in violin playing, actually, the actual intensity level of something matters about as much as how you do the vibrato. Because what you perceive as loud or not is really integrated and, in a much more complicated way. It depends on what kind of music you're playing. If you're playing a string quartet, it's going to sound quite different what a fortissimo is than if you're playing, a big symphony. Certainly a crumhorn and a trumpet, well, what the idea there is of what's a loud note or not is going to be totally different. The style of music really matters. So many different things matter that this idea is really quite misleading. I left it there because it was there on the original, and it's some of the most brilliant psychoacousticians, referenced all the time. Boy, this is 90 years ago now. It's still great work. On the other hand, yeah, everybody does dumb things, and that's a dumb thing. I think what they were trying to do here is similar to the thing I was doing before. I was trying to say, well, intensity level, is kind of like quiet speaking. And, obviously quiet speaking is kind of iffy too, but hey, got to say something. We good? Yeah, so don't get fooled by that. You know all these things, right? It's very complicated. Even just from physics of instruments, like how loud something sounds. If you have a piano recording and the person playing really loud and then you turn down the volume, is that a loud piano or not? I don't know. You can't even answer that question because, yeah, the volume might be turned down, but it doesn't sound like a piano playing quietly, right? So the whole thing is a bit of a iffy proposition there. All right. So now we have one more unit. We have we've done all the I's and in two positions, and now we have to do just one L. So if you leave off the level and you just say L, then that's loudness, and that's different than loudness level. And this is loudness and sones, and this is just yet a little bit cooler than the phones we just did, than the loudness level. So what is the deal here? Loudness, the phones units or the loudness level thing tells you about things that are equally loud, right? Those equal loudness contours, that's like, you know, a topographic map where you have equal feet above sea level, right? So that's what that is. Well, this is yet cooler here. This isn't just telling you this is louder than that or equally loud or less loud. You can actually compare how much louder. Twice as loud, 3 times as loud, 4 times as loud. And that is really cool. So, when you do loudness, now loudness is actually not used as often, I think. Sones are used less than phones. Phones are good enough for lots of things. So I'm not putting them down. That was really cool what we just did. But this is yet one step further where if you want to, if you have a loudness and sones, if something is 2 sones, it's twice as loud as 1 sones. Or if something is 1 sone, it's twice as loud as 0.5 sones, which is incredibly cool. So this is just a conversion between the two. And again, look at these axes, right? Sones here, we have this logarithmic thingy going on. In phones, at least it looks kind of linear in phones. So this, again, loudness level in phones, that was the previous graph's output. So from the graph here, another question of graph reading. You can do this. Just watch out here. See, this is 0.1, and that's 1. So what's this line here? That's 2, right? It's not 1.1 or something weirdo. So just be careful that you don't make dumb mistakes. Everybody does, but you know, it's unfortunate to do so when you're being time pressure tested. My question to you here is, this is a pretty straight line up here. So once you're above 40 phones, how many phones does it take to double loudness? Anybody got a guess? You guys can write something in from home too if you want. Yeah. You got to do better than that. That's really close. I don't mean that, but 10 is rounded to the nearest thing. Is it more than 10 or less than 10? So the answer was 10, which is clearly doing it right. And actually, you know, it's a silly question. Is it more than 10 or less than 10? But actually, when you're first doing this, especially when you're on the spot, it's really confusing. So let's just look at 40 here. When we go from 40, that's at 1 sone. So 2 sones would be twice as much, right? So that's actually a little less than 10. So we say 9. Or, I don't know, say 8.5 if you're feeling extra smart. I don't know how many digits of precision you're going to get off this glory graph. But in any case, it's about 9. And it's interesting, if you go up, say you are at 50, okay? That's just below this line here. And what is that line? That line is 2, 3, 4, 5. So it's just a little bit before 5. So you're a little bit below 10. And sure enough, that's about 9. It's consistent all the way across. It's just horrible to read these these funny graphs. Really, graph reading is something you probably did in high school and were good at one point. But yeah, it's just sort of there. And of course, you can just type it into Google, and I'm sure they do the conversion for you. Actually, I don't know. I don't know if they do phones to tones. They do femtoparsecs. That was a good one. Back when I used to play underwater hockey, we used that. Anybody know how far, what the distance is of a femtoparsec? It's a good distance in underwater hockey when you're working hard, holding your breath. It's about the length of a swimming pool, maybe 20-some yards. I don't know, something like that. So do you know what a microcentury is? It's about a class period, about 50 minutes. So if you ever, so anyway, there's lots of silly units like that. But and certainly Google does those conversions, I think. Okay, see, everybody knows what a millihelen is, right? This is like an old comedy routine. But Helen of Troy was so beautiful they launched 1,000 ships to go get her. So the amount of beauty it takes to launch one ship is a millihelen. Anyway, that's, I don't know, phones and phones are pretty weird, but maybe better than that. Okay, so why do I remember that one? I can't remember what day of the week it is. I don't know. Okay, so this is cool. And you see down here at lower volumes, it changes. So this is especially important if you have low volume things, is to figure out, well, what are totals, right? And they may matter. These kind of psychoacoustic things might even matter. Say you're making a dishwasher, and say you actually, you're going to have some motor whine, and you have a choice. Does it whine at these two frequencies, or does it whine at a single frequency? And how loud are those, and how will people perceive that? And if you have a choice in your design, it's kind of nice to be able to figure it out and to work on this. So what I would say is here, let's see what I say here. 2 versions of problem 3 on the sample midterm. By the way, in your course review, if you really hate these questions in the midterm, you can say so. People generally have trouble with conceptual problems. Anyway, on the midterm, if I ask you this question, or a question like this rather, I won't ask you exactly this because that would be cheesy, but mark your points on the graph so that when you misread the graphs, we can say, okay, well, -1 point, you read the graph wrong. But like, and this problem here, and the first one, the first version, problem 3, basically what this amounts to is you want to figure out total loudness, and you can't add up loudness levels. That doesn't work. You have to convert to loudness units and then add them up. And that's all the point of this is. So you can look at this when you study for your exam if you like, but you can add up loudness level. Now, even the loudness level, you got to be a little bit careful with these units because they're for significantly different frequency sinusoids. So anytime you start having real sounds, you got to remember there's a lot of different sinusoids there, and the combination of them have to be treated. Not just one. But anyway, if you have significant, like motor whine or something, if there's significantly different frequencies, you can certainly add that up. Here's another example of where you convert to Sohn's unit, but then they want to answer back I'm trying to dissociate myself from being the implement of torture. I wanted the answer in phones. You'll also notice the person got full credit and actually the answer was wrong, but happens too. Those are the re-grades you don't ask for. Yeah, so there we go. Okay? So, and these are straightforward things. If you've got questions, go ahead and ask in Piazza, or if you prefer, email. If you email, for things, it's usually best if you email all of us instead of just me or something, just so that somebody answers your question. All right, questions about this now. So you got intensity level, you got intensity, you got loudness level, and you got loudness. All these funny units. Okay, so here's a cool circuit. For those of you who are into circuits, this is really cool. Nowadays, actually, clever analog circuits, it's funny where they exist. Like if you're designing chips, there's all sorts of things in a digital chip that we have to worry about the analog nature of the world. So you may run into that. Certainly people that design power circuits and such are very good at really carefully selecting a small number of components and doing it. And people that do analog synthesizers. So there's still places they're used. This is a circuit that you would see, say, in the analog synthesizer world, and it used to be on every stereo. You know, this is just a really standard kind of circuit. There's a few different variations of the circuit, but I want you to know about this loudness circuit because it's cool. Is it scientifically deeply based on the facts we just had? It's related, but it's mostly based on the fact that, hey, you want to only have 2 capacitors and a resistor and make your thing sound better and have a cool button that people can press. And that's more what it's doing. So there's only 3 components here. There's a switch to say, do you want the loudness circuit on or not? And if you look at old stereo, say your parents or somebody still has an old stereo sitting around, you'll notice the loudness switch, it's still plugged in, it's still pushed in. Everybody pushes it in when they buy the thing and say, ooh, that sounds better, and then they leave it there. That may be an exaggeration, but I think it's pretty close to the truth. So, but yeah, this switch here is just for the loudness button. Do you want this turned on or not? And then there's 2 parts of the circuit here, but it's kind of interesting how this works. So you've got a volume knob here, and you've got this resistor pot, right? That's the volume knob. It's probably audio taper, you know, some sort of logarithmic or at least squared sort of ish resistance. So it's probably not just a linear resistor. But anyway, in the middle of it somewhere here, you have this connection here, and so when your wiper, when your volume is at low volume or high volume, your sound gets processed a little differently. When you're at really high volume, like you might be when you're driving your car because, you know, there's too much road noise. They just redid the surface of the road or something. Then there's this thing here that when you turn up the volume, as you turn up the volume, it actually brings in more highs. You can see here, right? This passes highs, and when you're upper part of the circuit, you get in more highs, high frequencies. And that's actually, why do that? Well, in general, when you have acoustic sounds, right, if you play louder on your violin or you play louder on whatever instrument you're playing, you tend to just, in some very fundamental way, have more high-frequency content, stronger high-frequency content. And that's true of almost all acoustic instruments. That's true even of your voice, right? So that's kind of cool. So that's sort of a physics of instrument things. When you turn up the volume, you want it to sound at least a little bit like somebody's actually trying to play louder, because it just sounds good. You know, even if you're at home and you're, you know, in your family room or wherever you're sitting, and you turn up the volume, it just sounds nice. You know, it actually sounds like there's more volume change than there really was when you do that. So that's kind of funny. Is this a really arbitrary sort of thing? Of course, you don't know how loud the original recording was. You're messing with the sound in this way, but it's not a hit you over the head effect, and it's okay. You know, you're probably not sitting in a listening room with sand on the walls and stuff anyway. So hey, there's all sorts of things affecting your sound. But then this bottom one here is actually something that's more psychoacoustically based. This one's here more, you know, what you would expect from physics of instruments. The bottom one is just to boost the lows. And that's, well, if you turn down the volume, you don't want your bass to drop out. So you boost it. Now, as you saw in the equal loudness graphs or the loudness level in phones graphs, you know, if the bass is already quite loud, then this might be overdoing it because it's only quiet low things. So the effect isn't real strong. You don't make these circuits, you know, hit you over the head. They just sound somewhat better. So it's just sort of a trade-off, and uses very few components and kind of cute. Questions about that?